Good morning, every one of you.
Good
Good
morning,
morning,
sir.
sir.
Hi. My screen is visible, PPT.
Yes,
Yes,
sir.
sir.
Yeah, okay. Today there's no network Wi-Fi in the college, so I'm using mobile net. So just bear with me. I can't open this OneNote also today. Okay, we are going to see this unit 5, which is extraction. So what is this extraction? How far it is different from this earlier chapter, which is leaching and as well as distillation. So leaching, I hope you probably understood the every concept in the leaching. In the leaching is nothing but solid to liquid operation. Why? Because in the leaching solid is there. Inside the solid, solute is located. So that inert solid, whatever the solid content, which is not at all soluble in any solvent, is called as inert solid. Inert solid plus solute present in that solid is just given to some solvent, and that solvent will go inside, and then it will bring that solute component from the solid, uh, and leaves the solvent in the solvent rich phase with a solute composition into it. So because of that, the solute which is present in the solid is just taken by some solvent. Because of that only we are calling it as solid to liquid operation. Now, what is this extraction? So, preciously, we can call this as liquid extraction. Why? Because in the liquid, now there is no solid concept here. In the leaching, solids are there, but here two immiscible liquids are there. There, if you see, solid is there, one phase, and another phase is a solute or a solvent, which is another liquid phase. But here it is only two liquids are there. There is no solid phase here, but inside this liquid only there is two immiscible phases are there. Because of this, it is called as liquid extraction. So why? In the first liquid, if you see, we will consider one solvent or one solvent which is associated with solute. So A plus C, then some B solvent will be coming here. So inside this one, if you see the feed solution or a heavy phase, we can call this one. Inside this feed solution, one solute and one solvent will be there. Okay, one solute and solvent will be there. This solvent is nothing but the solvent which is associated with this solute particles. Okay, if you consider this what with green lines as a solute and this red lines as a solvent. So this red line is this red dots is nothing but the solvent which is associated with this solute. Okay, and another solvent which is called as a light phase will be just added to it and allowed to mix or disperse. One phase is dispersed into the another phase. Okay, what is continuous phase, what is dispersed phase, it will be decided by the operation of that particular equipment. Okay, if we are using some spray tower, in the spray towers or a packet tower, there are two types of operation. One is making this heavy phase as the dispersed phase, and another type of contact is making this solvent or a light phase as a dispersed phase. Okay, when this is dispersed phase, then this solvent or a light phase is a continuous phase. When this solvent or a liquid phase is a dispersed phase, then this feed solution or a heavy phase will be the continuous phase. Okay, it will completely depends on the particular equipment which is there. Now after dispersing with some agitation or something contacting pattern of packet bed or a spray tower, something contacting pattern. Okay, after associating this two solvent and this feed solution, after allowing them to come into contact, after that what will happen, the phase will be separated out, nothing but a decantation operation. Okay, you might have seen in the fluid mechanics course. So decantation operation is nothing but based on the density differences of two phases or two liquid phases. So that two phases will be separated out. One may be just floating above that one may be in the bottom side. So phase separation will happen usually in the decantation setup. So this will be a settling and this will be a mixing. So this is a mixing process in which one phase, one dispersed phase will be just going into the continuous phase, and there will be some coalescence will happens. Then this dispersed phase will be solubilized into this continuous phase. Then mass transfer will takes place here, and after this mass transfer, these two phases, This intermittent phases will be just allowed to settle in some decanter or in some settler. After allowing that one, a two-phase separation will be possible. One phase is called as an extract phase, which is a solute rich phase, and another phase is called as a solvent rich phase or raffinate phase we can call. So now here if you see the extract phase is our main product because solute is coming here. If you compare this with earlier case leaching, in order to differentiate, keep some difference between these two, leaching and extraction operation, there we consider raffinate as our product, main product. Why? Because in the raffinate itself solute is coming, whereas inert solids are coming in the overflow, coming in the underflow, or this one, extract phase there. So inert solids are coming in the extract phase there, so it is not a desirable product there. But here the extract phase is a desirable phase which is having a more solute. Because of this extraction, we have kept this extract as our desirable product, whereas raffinate is undesirable. The solvent which is associated with this in the heavy phase will be coming more into this raffinate phase. So this is the concept behind this one. There's two difference in leaching and extraction. One is this one, solid to liquid operation there. So because of solids are there, inside the solid some solute is there. The solute is coming in contact with a fresh solvent. That fresh solvent is just taking out that solute from the solid, and it is coming out as in a raffinate phase there in the leaching. So that is called as a leaching operation, which is a solid to liquid operation. But here there are two liquids. There is no point of solids here, but the two liquids are also in a two immiscible liquids. These are two immiscible liquids. Because of this, we are calling it as two phases. So one is a heavy phase, which is a feed solution phase. Already in this heavy phase, there is a solvent which is associated with solute. This is a different solvent. Okay. Then a fresh solvent, or we may call this as a light phase. When they come into intimate contact, and it will be mixed in a mixer or a mixer setup with some external force or with some contacting pattern, then what happens, one phase may be a disperser phase, another phase may be a continuous phase, depending on the mode of operation of a equipment. Then the disperser phase is just solubilizing inside this continuous phase. Then after dispersing the disperser phase into the continuous phase, then these phases are allowed to settle in some decanter or some settler. Then what happens, two phase separation will be takes place using the density difference or by the gravity or by some centrifugal actions. So the decantation, the separation of two phases will be carried out because of the density difference. Okay, whether we are applying an external force like a centrifugal force, then it is called as a centrifugal settler. When we are diving or nothing but a sedimentation process in your mechanical unit operation. So in order to happen this extraction process, there may be two phases which are immiscible. Then these two phases will be coming into intimate contact by some agitation or by some contacting pattern, and after mixing the two phases will be separated in a decanter setup. So this is overall what is happening inside the leaching operation. Okay, if you have any doubt, you can ask me. Then I will move to the next points. Is it okay?
Yes, sir.
Yeah.
Sir.
Shall I move to the next one?
Yes, move, you can move, sir.
Yeah, thank you. Okay, then contents. What are there the contents? Then we have seen what is the concept behind this leaching operation and the differences between the earlier leaching operation and the extraction operation. Now, according to your syllabus, these are the contents which are involved. So the contents are extraction equipments. So what type of equipments we will use? Some of the equipments they are listed out here. So one is a mixer settler setup they will use, and next one is a spray and packed extraction tower, then perforated plate towers, and then baffle towers. This is there for your syllabus. Apart from this, there are many equipments are there for the leaching to carry out this extraction operation. But out of this, this is very limited content is there. So these are the equipments. So mixer settlers, spray and packed extraction towers, perforated plate towers, and a baffle towers. We'll see this one. Then principles of extraction, equilibrium and phase compositions. So we have seen what is the principle behind this extraction? Some solvent is coming, a third solvent is coming, and that solvent is solubilizing the solute, and they are just allowed to settle out in two phases. That one phase is we are collecting as the extract phase, another phase is collecting as a raffinate phase. That is nothing but extraction, principles of extraction. Then after that, equilibrium, how these two phases are reaching equilibrium. Without reaching equilibrium, whether we are separation is possible, after reaching is equilibrium only separation is possible, we have to see. Then phase separation or a phase composition. After phases are separated out, what fraction of solute which is there in the extract phase and what fraction of solute which is there in the raffinate phase, we have to see this one. Then triangular diagram. So since here if you see there are two immiscible phases are there and the three components are there. Earlier in the leaching chapter, what we have done, the B free basis means inert solids we completely neglected there because it is completely inert. But here there is a possibility that the solvent which is associated in feed may be solubilizing with the solvent itself and may be associated with the solute itself. So because of this, the basic diagram here is a ternary diagram, nothing but a triangular diagram. Okay, equilateral triangle we will use here in order to evaluate the compositions. Why? Because when you locate two compositions on an equilateral triangle, the third composition we can find very easily. So because of that advantage, the basic diagram which can be used in the extraction process is this one, triangular diagram. So this triangular diagram can be used in the leaching also, but there in order to lower the complexity in using this triangular diagram, we made that B-free basis. So every terminology, every notation scheme which we adopted in the leaching is on a B-free basis. So B-free basis, we just neglected the third component. Because of this, only two components are there and two-dimensional, two-coordinate system graphs we have taken. But here we can't neglect the A phase also, solvent phase associated with the feed stream. So we have to take the basic diagram, which is the triangular diagram. So how to evaluate the triangular diagram, we will see. Then equilibrium line, plane point. Okay, what is this equilibrium line? There is also equilibrium line is there, tie line is also there. On the tie line, some mixer point we have located. Like this here, the plane point, we will call that as a plane point. What is this plane point? We will see. Then next one is the same as the leaching, single stage operation is there. Here also single stage extraction operation is there. Then multi-stage cross current extraction for miscible system. So what is this miscible system? What is immiscible system? So there are two types of system here. One is miscible system, meaning if you see the solvent which is associated with this one, the solvent which is associated with this feed solution, whether it is miscible with the solvent which is freshly coming or not, whether that is miscible or whether that is not miscible. Based on that one, we have to fix a criteria whether the system is miscible or immiscible. So here, as that of a leaching, there is a multi-stage cross current extraction is also there. So in the leaching also multi-stage cross current leaching cases. One is a miscible case, another one is an immiscible case. So similarly, multi-stage cross current also, one is a miscible stage is there, another one is a immiscible stage is there. So this is not given in your syllabus. Immiscible cases for the multi-stage cross current. Then here the next one is a continuous counter current multi-stage extraction. As such, it is also there in the leaching operation. So here the terminology will be somewhat different. So if you compare with the leaching operation, there is a single stage leaching operation, like that here also single stage extraction operation. There is a multi-stage cross current leaching operation, here also same multi-stage cross current extraction operation. So there is also in the leaching, continuous counter current leaching operation is also there, but here it is continuous counter current multi-stage extraction operation is there. But only the difference here is one is a miscible system. For every type of equipment, like a single stage or a multi-stage, for every equipment there are two cases. One is miscible case and another one is immiscible case, insoluble or immiscible case. One is a miscible case and another one is insoluble case. Then the problems we have to see that one. So it's up to you. You want to solve a problem or not. But basic recommendation is you don't start this type of problems as such in leaching also, in the extraction also, because it will waste your time to a lot extent. So better to choose the problems in unit 1, 2, 3. So after that one, don't start. If you know that problem, we have taken that in the classroom itself, you can directly guess that value and you can go. Otherwise, the trial and error methods are very difficult to solve. So these are the only contents. Then we'll see what is liquid extraction. So liquid extraction can also be called as a solvent extraction. Why? Because the solvent we are using to separate here, and also called as a partitioning. Why? Because there are the feed solution contains two compositions. One is the solute itself is there, and one solvent is also there. That solvent and solute are separating out, nothing but partitioning in between two phases. One is raffinate phase and another one is the extraction phase. Because of this reason, this operation is also called as a partitioning operation, and because we are using a solvent, third solvent for this one, because of this we can call this as a solvent extraction process. So liquid extraction is the separation of the constituents of a liquid by contact with another insoluble liquid called solvent. So liquid extraction is constants of a liquid by contact with another insoluble liquid. So this is insoluble liquid. Inside this also feed some solvent is there, which is not at all miscible with this one. That's the condition. The constituents get distributed between two phases. So these two phases, they are distributed. The solvent-rich phase is called as extract phase. So this is our main product phase. The solvent, all the solvent which is coming to the extraction unit, it is collecting some part of solute from the feed and coming as the extraction phase, extract phase, or extraction phase, or extract phase we can call. Then and the residual liquid from which the solute has been removed is called as raffinate phase. So this is solvent lean phase. This is solvent rich phase. So raffinate phase is a solvent lean phase, and this is extract phase is a solvent rich phase. Whereas in the leaching, if you compare, there this raffinate is a solvent rich phase and this extract is a solvent lean phase. So the terminology, you just understand the terminology. In the leaching operation, we have kept raffinate as our main product. Because of that, it is called as solvent rich phase. In the extract process, as the name indicates, in the extraction process, as the name indicates, extract is our main product. Okay, extract is our main product here. Okay, extract is our main product. Because of extraction is its terminology. So this is solvent rich phase here, and this raffinate is solvent lean phase here. So what are these parameters? F is feed. Okay, we know this one. Here B is a solvent, or we can denote it as S also. Solvent, yes, we can take. But the composition, the notation scheme which we apply here is feed will contain a pure what we say, this pure liquid. Okay, pure liquid is nothing but the solvent, the liquid which is associated with this solute C. Here also solute is denoted by C, but there in the leaching, if you see, B is we have given for the inert phase, inert solids, but here B is given for the pure solvent. Okay, this one pure solvent. Okay, this solvent is different from this solvent or this liquid. This liquid is different. B liquid is a pure solvent which is coming here, but this A is nothing but which is there already in this feed stream along with the C. A plus C is going from the feed, and this B is collecting this C and coming in the extract phase, whereas the A which is there in the feed which is coming here in the raffinate phase. That's the concept here. So here the terminology, if you see, small y is nothing but mole fraction, and this capital Y is nothing but mass ratios, or small x is nothing but mole fractions, and capital X is nothing but mole ratios. So mass ratios. So what is this one? So mass fraction, we already know that one mass fraction of solute in the feed and raffinate phase means, what is this mass fraction? Mass of C divided by mass of A plus B plus C, if B is also somewhat there in the feed. Then in the raffinate phase also, X is equal to C, mass of solute C divided by mass of A plus B plus C. So that's it. How many components are there? So denominator, that many components will come. So that is a mass fraction. X and Y also same. The small y is a mass fraction. So mass fraction of C solute C divided by A plus B plus C. If A and C also there in the solvent, it is not a pure solvent then. Then in the small y also, mass of C divided by mass of A plus B plus C, if all the three components are present there. Then what is this capital X? Capital X is mass of solute, means C divided by mass of solute free component in feed or raffinate. So mass of solute free component. So mass of C divided by mass of A plus B. So we have to neglect C here in calculating this mass ratios. Since those are mass ratios, so one component which we are considering in the numerator, we can't take that part in the denominator. That's the criteria here. So y also say mass of solute, which is C, divided by mass of A plus B, excluding solvent, excluding this one, solute component. So this is extraction, overall notation scheme. If OneNote is working, then I will show. If not working, just tell to me. Yeah, here if you see, this is one liquid and this is solute. So we are using this notation, and some B is there. This is also one liquid, but we are calling it with a separate name here, which is solvent. So feed is composed of feed liquid. Here there is no solids. So feed liquid is composed of A plus C. So this is the liquid which is associated with the solute. So earlier in the previous case, what happens in the leaching? So B is the inert solid plus some B is there, which is there in the feed stream. So the operation has to carry out, what operation has to carry out? Some solvent is coming here, which solvent we are indicating with some A. So this solvent is coming, and what it is doing, this solvent is carrying this solute and leaving in the raffinate phase, and the B inert solids are there. This inert solid is completely coming in the extract phase in the earlier leaching. But in the in this one, now what happens? A plus C are going inside some extraction unit, and after that some solvent which we are denoting with B, this solvent is coming and this is leaving in the, now the main product we are calling as a extract phase. So this B, whatever the B is there, this B and this C is coming out in the extract phase, and whatever the A is there, which is going in the raffinate phase. So this is what happening here. So in the earlier case, it is B is completely inert. This one is B is completely inert. So because of this reason, in every calculation, we have neglected this B. Why? Because it is going to stay the same as such. It is not at all variable. But here it is not like that. This is immiscible. Somewhat miscibility will also be there in the solvent. So that is called as a miscible system and immiscible system. So we can't neglect this A. So when you are considering this x, small x means C by, if A plus C is there, then A plus C. If some B is also there along in the feed, so it will be A plus B plus C. So capital Y, capital X, the difference is here C, mass ratios, C by A plus, if B is there, B we have to take, but we can't take this C. Why? Because it's a mass ratio. So now X is equal to C by A plus B. Same, similarly, same one, Y if you are taking small y, if you are taking, so C by, if the B plus C is there, we can take B plus C, or otherwise if A is also there, some fraction, B plus C plus A. If capital Y is there, capital Y is nothing but it's a mass ratio of solute to other components, C by A, B plus C, or otherwise if not C, C by B, or otherwise some fraction of some amount of A is also there in that one. So we can take B plus A. Like this we have to take. So this is a notation scheme difference. Capital Y and capital X are different, and this capital X, small x and small y are different. So these are more mass fractions. These are mass ratios. So small y is mass fractions with respect to solute only, small y and small x. but capital Y and capital X is mass ratio on C free basis or a solute free basis. This is what going to happen in this one. So is it okay, the notation scheme now?
Yes, sir.
Yeah. Okay. Then next one, why there are many separation operations, mass transfer operations. Why we have to use this new operation, which is extraction operation? What's the purpose of this extraction operation? So purpose of this extraction operation is whenever there is a closed boiling point mixture is there. Okay, the components A plus C is there in the initial feed mixture. So these two are only liquids only, that also. So solute C plus this liquid A is also liquids only. But instead of directly giving it to the distillation, why another operation extraction is we are taking? Because this A is also having some boiling point. For example, 100 boiling point of A, and C is also having a nearly 99 boiling point or 98 degree centigrade boiling point. Then what happens? There is no much difference in between the boiling points of these two components. Then what happens? The separation using distillation is very difficult. So the separation using distillation is measured using relative volatility. So when the boiling points are very close enough, so each component of the mixture has a very close enough boiling point, then what happens? The relative volatility will be very, very low. So relative volatility is very low means, so separation by distillation is difficult, plus relative volatility is near equal to 1 means what happens? Separation by distillation is not at all possible. So they may be relative volatility may be nearly equal to 1. In such cases we have to use one another operation, extraction. Since this extraction is a secondary operation, after separating using some solvent, that solvent has to separate once again. To separate that solvent, we have to use once again the distillation. So it's secondary operation. So distillation will be a primary operation. It's a ultimate purification operation, the final purification operation. But it's a secondary purification operation. After passing through the extraction column, the solvent which have used in the extraction has to be once again separated using the distillation or something other operations. So the purpose of this extraction is, first point is to separate the close boiling point mixture. Why? Because when there is a close boiling point, the relative volatility will be very less. So difference between the boiling points are very less, the relative volatility will be very less. Then the separation by primary separation column, which is distillation, is very difficult. Because of that reason, we have to use extraction. Then the mixture that cannot withstand high temperatures of distillation. So distillation is a temperature intensive process. We have to give thermal energy to that one. Based on that thermal energy only, the separation is possible. But here there is no need of thermal energy. Using some third component or some solvent, we are able to separate it out. So when the materials which are used for the separation, which are there in the feed, are very heat sensitive materials. So what happens? There might be a possibility of thermal degradation. So thermal degradation, to lower the thermal degradation condition, we have to use one step which is called as extraction. So mixtures that cannot withstand high temperatures of distillation. Why? Because there may be a thermal degradation of the components inside that mixture. Because of that reason, we have to use extraction. Then the next one is temperature sensitivity of the products. They are both are very much related. So they cannot withstand, and thermal sensitivity also same. Then high purity requirements. So high purity requirements, distillation, if you see, when the boiling points are very close, the separation of distillation is not at all possible or difficult in possibility, but at the same time the purity will be very low. So in order to increase the purity compared to that one secondary operation in between will be added, that is extraction process. After that one, once again distillation if you do, there may be a boiling point difference between solvent which is used during extraction and the solute which is there. So almost a pure solute can be obtained in this extraction process after passing through one stage which is extraction process. So high purity requirement. So if you have a very high purity requirement, we have to use one more step which is extraction in between distillation and final product. Then high boiling point species in low quantities. So whatever high boiling, but they are very minute quantities. Then what happens? Separation by distillation is very energy intensive. That may be very costly. So under that cases, we can use this extraction process. The need to separate by species type. So rather than relative volatility, only it is dependent on the solubility. The separation is entirely dependent on the solubility. Then what happens? Extraction process we have to go. Otherwise, when they have a large relative volatility or they are dependent on the boiling points only, we can go for the distillation. So when there is a need to separate by species type rather than this relative volatility, we have to go under such conditions. We have to go extraction. Then close boiling points but high solubility difference. So very close boiling points are there, so this was covered in the first point, but high solubility difference. So a plus c is there in the feed mixture. When the third component like b is adding, when there is a solubility difference of this a plus c in the b, what happens? We can say that there is a solubility difference between a plus b and c plus b. Then under such conditions we can use the extraction also. So solubility difference, based on the solubility difference only, we can separate it out by the extraction. Then azeotrope forming mixture. So if you see azeotropic forming mixture means the mixture will have a constant boiling point. The mixtures, whenever we are separating that azeotropic mixtures, whatever the mixture, whatever the composition of mixture in the distillate is there, that same composition will be there in the residue also. So azeotropic mixture is nothing but a constant boiling mixture. So the boiling point will be somewhat a single boiling point will be there. When we carried out the separation, the compositions in both this residue and bottoms are this one distillate phase, both are same. Under such conditions, to break that azeotropes, a third component we can use. Same we have seen in the distillation unit 3, which is extractive distillation. So extraction plus distillation is called as a extractive distillation. Using some third component or entrainer, that third component is called as entrainer. We have seen that separation. How can we carry out the extractive distillation? So under such conditions also, to break the azeotrope between two components of a mixture, we can use extraction. So this is the purpose for which extraction is used. When there is a difficulty in separation by a primary separation unit, which is a distillation, then for all these reasons we can carry out extraction. This is the purpose. So then examples. What are the examples? The commercial examples, industrial examples which are there. Now the extraction is carried out on a major separation basis. So extraction of acetic acid from acetic acid water mixture using ethyl acetate. So ethyl acetate here is a solvent, so which is B, and this acetic acid will be a solute, which is C, and water is the solvent which is associated, or a liquid which is associated with a solute, which is A. So acetic acid is a C, water is A, and solvent, this ethyl acetate, is B. So this is separation of or extraction of acetic acid from acetic acid water mixture using ethyl acetate as a solvent. So this is one example of industrial applicability. And next one is extraction of acetic acid from acetic acid benzene mixture using, in this case, the water is a solvent. So this is B, and this is acetic acid is C, and benzene is A. This A plus C are going, and this C is coming out along with this B. So finally in the extract phase, this B plus C is coming. So this is one example of industrial applicability. Then extraction of acetone using acetone water mixture using chloroform. So this chloroform is a solvent. So according to our notation, this is B. And water, which is a solvent which is associated with the solute. So this water is A, and this acetone is C. So C plus A is going, and this B, a third solvent, which is a chloroform, which is coming in the extraction column, and it is separating out this acetone and coming in the extract phase. So this example, and next one is a separation of fission products like a uranium separation. Since they are very low grade materials, so separation by distillation will be very much advantageous under that conditions. So separation of fission products from nuclear energy process and the separation of low cost metals can be effectively carried out by liquid extraction. Okay, irrespective of any solvent. Okay, depending on the particular condition, solvent can be used, but separation of uranium products also, extraction is very possible. And for many ore separations, like in metallurgical operations, many metals will be separated using this extraction process only. So extraction will have lot of industrial applicability. Then next one is the pharmaceutical products like penicillin, penicillin G cap be extracted from aqueous fermentation broth. So fermentation, inside this fermentation broth, this penicillin will be there using immiscible organic solvent like amyl acetate. So amyl acetate will be this solvent here, and penicillin will be a solute, and aqueous phase or a water will be the solvent which is associated with the solute. So under these conditions in the pharmaceutical industry also, this extraction has a many applicabilities. Then phenol is extracted from charcoal. So phenol is extracted from coal tar using alkaline solution as solvent. So alkaline solutions, maybe the solvent NaCl or something. So maybe a solvent. Then phenol is a solute which is C, and this is B, and coal tar will be an A, which is associated with phenol. To separate a phenol from the coal tars, so alkaline solution will be used as a solvent. Then aqueous caprolactam liquor. In the liquor, caprolactam will be there. This is a solute, and aqueous means water will be there. So will be extracted using benzene as a solvent. So benzene will be a solvent which is C, and this caprolactam will be our solute which is C. Then aqueous means water. Water will be the solvent which is associated with our solute which is A. So A is water, and this C is caprolactam, and B is benzene here. So these are the popular examples, industrial examples, where the extraction process can be used. So then next one is a dual solvent or double solvent or fractional extraction. So what is this concept? Okay, whenever the complicated systems of extraction process is there, then we have to use two solvents. So two solvents has to be used rather than one solvent. If you notice all these 7 examples, only the single solvent is there we have used. So this extraction process are not at all that much complex. But what happens in the dual solvent or double solvent or the fractional extraction process, because of the complexity of the separation process, we have to use double solvent or two solvents we have to use. So under such conditions, we can call that process as a dual solvent process or the double solvent process or a fractional extraction process. So what is the example for this type of separation? So this one, a mixture of para or orthonitrobenzoic acid. So para and ortho, these isomers are there. These isomers separation can be separated by distributing them between insoluble liquid chloroform and water. Here the chloroform and water will form the two solvents. So one solvent will be just dissolving one isomer, and another solvent will be just dissolving another isomer. So para isomer will be dissolved by this chloroform, and ortho type of isomers will be dissolved by this water. So under such conditions, the process is called as a dual solvent or double solvent or a fractional extraction process. Okay, these are the examples. Is it okay? Up to the examples, purpose and examples. Shall I move?
Yeah, sir.
Yeah. Okay, then now we understand the concept of this extraction process and where the industrial applicabilities are there. Why we have to go for the extraction, we understood. The purpose of the extraction, we understood. But now we have to think about the steps which are carrying out in the extraction. So all the steps, what are the steps which are carrying out in the extraction? First, if you see, same figure. So yeah, the first step in carrying out in the extraction process is we want mixing. We have to do some mixing after adding some solvent, suitable solvent to it. So we have to have a mixing. So that is mixing or contacting is the first step in the extraction operation. Why we have to mix? To have a coalescence of this dispersed phase into this continuous phase. So to coalesce the dispersed phase into the continuous phase, we have to provide some external aid. So some additional force we have to provide. That additional force can be from the liquid-liquid contact, or that additional force can be from some suitable agitator, or that additional force can be due to the turbulence created by some baffles. So maybe anything, depending on the contacting equipments, we can induce some turbulence into it. When turbulence or a mixing intensity increases, what happens? Obviously, the phase miscibility will be very high. So in the normal miscibility, when you without a digitation, when you left out something, so to solubilize one component into other component, it will take years and years. When the turbulence has been increased between two phases, what happens? The solubility will be very much increased. So because of this, So mixing and contacting has to be happened so that it can create some turbulence between the two liquid phases. So this is the main aim. So after contacting with this one and agitating, what happens? A small droplet dispersion in a continuous phase. Then this agitation or this turbulence created by inside will help this disperser phase in order to impinge into this continuous phase. So this is the mixing process. So which phase is disperser phase? Depending on the equipment mode of operation. So we have to fix whether heavy phase is the disperser phase. When heavy phase is the disperser phase, then this light phase is a continuous phase. When light phase is the disperser phase, then heavy phase will be a continuous phase. So this two only these light and heavy phases are there. In between these two phases only we have to fix. One is a dispersed and another one is a continuous phase, depending on the mode of operation of that equipment. So we will discuss during the equipments different type of equipment discussion. This one. So mass transfer between phases. So after just coalescing this one droplets into another droplets, what happens? A coalescence will happen. So a mixing criteria will happen there. A coalescence of these two phases will be happens. Because of this coalescences, what happens? The mass transfer will takes place from one droplet to another droplet, from one disperser phase to continuous phase. Then in the dispersion, what happens? One constituent from the one phase will be solubilized into another phase. Then only it is called as a mass transfer operation. Some mass transfer is taking place. Then how it is limited? So it is limited by the solute. Why? Because solute is the major constituent which has to be solubilized inside this solvent. So the solute will obviously will have a low solubility in the solvent. So because of this reason only we are using this extraction process. So the solute which is having a low solubility in the solvent will be the limiting step, rate limiting step. So in every process, any solubilizing process, the component which is having a highest resistance is a rate limiting or a mixing relating or a mass transfer limiting step only. So here the solute will be the mass transfer limiting step. So after a droplet is dispersed into one continuous phase, the mass transfer will happen. So here entire mass transfer is happening in the mixing section. Then after that, what we have to do, a phase separation has to be carried out. The next step is a phase separation. How this phase separation will happen? First is mixing. In the mixing, what happens? Two phases are just coalescing, just mixing with each other. So mixing we are. Now in the phase separation, in the next step, what we are doing, the reverse of that we are doing. Means the phases are we are separating. Now in the initial, when we are mixing the two phases, one of the constituent which is solute is solubilizing in other phase. From one phase to another phase it is going. Now after solubilizing, that two phases has to be separated out. So the next step will be phase separation. So reverse of the mixing process is called as this phase separation process. Then drops come together and coalesce. So here drops will be just detaching from one another. So after that only the separation is possible in two phases. Relies on density difference. To large extent relies on the density difference, whether it may be due to gravity or whether it may be due to some external force like a centrifugal force. We can apply anything, but the main step happening here is phase separation. Two phases has to be separated out. So one is solvent rich phase, another one is a solvent lean phase, or we can call one is solute rich phase, another one is a solute lean phase we can call. So either way we can call that one. So the component which is solute rich phase is called as extract phase, which is the main product in our extraction, and the phase which is a solute lean phase or solvent lean phase, we can call this as a raffinate phase, which is thus byproduct we can call in the extraction process. But in the extraction process, this extract is the main product here. So this one, the next step is phase separation has to be carried out. Then the third step is collection of phases leaving the unit. So we have to collect the phases. One is the extract phase, we have to separate it out, and another one is a raffinate phase. To collection of raffinate phase and extract phase has to be carried out. So there are three steps in the extraction process. One is mixing or contacting. The next one is a phase separation. Then after phase separation, we have to collect the two phases individually. So that's the major steps which are carrying out in the extraction process. Then what are the factors on which this extraction process is entirely dependent? So there are many factors, and this process is also called as a selection of a solvent for the extraction. So why we are calling this selection of a solvent for the extraction? Depending on the solvent only, the efficiency of the extraction process will be dependent. So if the efficiency of a solvent is very low, then the extraction process efficiency will be obviously very low. So main aim here is to recover as much as possible the solute we have to recover. So to recover that solute, we have to choose some solvent. So that solvent we have to choose using the solubility of that solubility of the solute in the solvent. So first criteria will be solubility of solute in the solvent. If the solubility of the solute in solvent is very low, then we can't separate that solute using the solvent, using the solvent. So first we have to evaluate the solubility. So solubility depends on many factors like selectivity. So what is the selectivity? So to separate out into, okay, the solubility of solute in the two phases is called as its selectivity. It is usually denoted by this beta. So selectivity. So selectivity beta is given by this formula, which is weight fraction of C by weight fraction of A in extract phase divided by weight fraction of C by weight fraction of A in the raffinate phase. The ratio of two constituents in one phase and the same ratio of two constituents in the another phase is called as selectivity. If the selectivity is very high, means this numerator has to be very high. So numerator is nothing but an extract phase. So in the extract phase, the solute composition needs to be very high. So how it can be very high? When the solvent is very much highly soluble in this solute C, then only the extract, because extract is a solvent rich phase. So obviously when there is a high solubility of this C in the solvent, then only the large part of solute is coming into the extract phase. Okay, then the denominator will be very low. Then the beta is also dependent on the, we can express this same beta or a selectivity in another terminology, which is weight fraction of A in the raffinate phase divided by weight fraction of A in the extract phase. So A is present in feed, A plus C. So our main aim is C has to come in the extract phase. So if C has to come in extract phase, means A has to go on the another phase, which is a raffinate phase. So here if you see weight fraction of A needs to be very much high in the raffinate phase. Okay, it must be low in the extract phase. Why? Because C has to go in the extract phase to a large extent. So because of this reason, weight fraction of A in the raffinate phase should be very high compared to the weight fraction of A in the extract phase. Under these conditions, we can say that concentration of solute in extract will be very high. So this is one definition of this selectivity, and another definition of selectivity is beta is this one. So usually we should prefer a solvent which will have a high selectivity, higher than unity. We have to go beta values higher than unity, then only the separation will be very high. So usually we have to select a solvent which is selectivity greater than unity. So this is the criteria. Okay, you understood this one, beta selectivity. What is the selectivity? If you understand in which phase what is coming and what is leaving in each phase, so then this will be very much better. So if you don't understand what is going in extract phase and what is coming in the raffinate phase, you will not understand these concepts. So beta is nothing but when we are comparing the extract phase, the C has to be very great, very high. When we are taking as a basis this raffinate phase, in the raffinate phase A has to be very high. So this is the criteria. Based on that one, we have to select our solvent. So selectivity of solvent is very much important. Okay, beta is okay.
Yes, sir.
Yeah. Then next one is a distribution coefficient. So distribution. So extraction is also called as a partitioning. Partition is nothing but the solute has to be partitioned between two phases. One is extract and one is a raffinate phase. The solution from feed has to be dispersed or just partitioned in between two phases, extract or raffinate phase. Under such condition, this is called as a distribution coefficient, which is defined as the concentration of solute in extract, which is denoted by Y, then the concentration of solute in the raffinate phase, which is denoted by X. So concentration of solute in one phase and concentration of solute in the other phase. So it is preferable to have higher ratio Y by X as it results in the use of lesser quantity of solvent. So why? Because K is directly proportional to Y. So Y is nothing but concentration of solute in the extract phase. Extract is our main product stream. So the solute in the main product stream has to be very high. Because of this reason, K needs to be very high. If K is very high, the limited amount of solvent with the limited amount of much less amount of solvent, we can carry out this extraction process. That's the advantage in having high distribution coefficient. So the solvent selectivity for the solute needs to be very high, and at the same time the distribution coefficient needs to be very high. Then the recoverability of the solvent. So recoverability, what is this recoverability? So after extraction operation, that solvent has to be separated out by leaving this solute. So then only one another purification process we have to add. Maybe due to the distillation, okay, when another process after extraction, maybe distillation we have to carry it out, because we have to separate out the solvent from the solute. So since B plus C is coming in our extract phase, now we have to separate out B from C. Since B is our main, C is our main product now. So to separate out this one, maybe distillation, one another step we are using. So to ensure the mixture doesn't form an azeotrope, we have to ensure that the solvent which we are using, which it cannot form an azeotrope with the solute. So C, B plus C does not form an azeotrope. If they are forming azeotrope means we have to once again do a same process. Once again we have to repeat. So if it is forming azeotrope means we have to repeat the same process when another additional step we have to add like this. So n number of additional steps we have to add. So we have to select a solvent that it should have a high solubility, but that solubility need not to form an azeotrope. If they are forming azeotrope between solvent plus solute, then that solvent cannot be used for the extraction purpose. So in order to have a recoverability of solvent very high, the solvent need not to be form an azeotrope, and solvent should have a high relative volatility. If high relative volatility is there, solvent can be just flashed or evaporated in the distillation column, and it will leave behind your pure component solute C. So then the recoverability of solvent will be very high if high relative volatility of a solvent is there, and then low latent heat of vaporization of solvent. So if the latent heat of vaporization is very low, then the separation by distillation is very easy. So we have to supply a minimum energy, okay, minimum amount of energy, so that the solvent will be leaving this solute behind. So that's the operation. In order to have a high recoverability of a solvent needs to be chosen in such a way that it does not form any azeotrope, and it should have a high relative volatility, and it should have low latent heat of vaporization. So these three criteria they has to satisfy. Then the density. So density of solvent will be different, and density of solute will be different, and density of A is also different. The solvent which is associated with the solute. So three densities are there. When all these components are mixing together in the extraction process, what happens? The density difference will come. So we cannot measure accurately what is the density of that particular mixture. Density difference will come because it might increase or decrease. We cannot say that one. So the density difference measurement is very much possible in this process, extraction process. So density difference should be greater as much as possible. If density difference is greater, what happens in the decantation process, this separation process? So density difference is very high, the separations will be, these phases will be readily separated out. If the density difference is very low, the phases will be miscible with each other. So it will remain miscible only. We have to apply some external force like a centrifugal force. So in order to lower the energy intensity of this process, we should have high density difference. So the density difference needs to be greater as much as possible. Then the next parameter is interfacial tension. So what is this interfacial tension? So how it is related to surface tension? So surface tension is nothing but the interaction, the tension between the gas and liquid phase. Okay, like air and water phase. Okay, the tension. Okay, the evaporation tension between this water and air. Okay, that is called as a surface tension. But the tension between the liquid to liquid, which are not at all miscible with each other, immiscible liquids, when two immiscible liquids are there, their tension between these two immiscible liquids for the solubilizing is called as an interfacial tension. when gas, one component is gas and other component is a liquid, the tension between these two phases is called as a surface tension. When the two components are the liquid itself, the tension between these two immiscible phases is called as a interfacial tension. So interfacial tension is very much important in the extraction process. So this interfacial tension needs to be very high in the వచ్చిందా రాలేదు సార్ ఇంకా రాలా ఇంకా వైఫై. So the interfacial tension between these two components needs to be very high as much as possible. Then if these interfacial tensions are very high in between this one, the dispersion of one phase to another phase will be very high. If this is very low, the dispersion will be very low. If there is no dispersion, there is no separation. That's the criteria. Then chemical reactivity. So this chemical reactivity, so the components, the solvent which we are using, it should be thermally stable. Why? Because once again we have to use some distillation inside that one. If we are using distillation, if they are thermally unstable, means they will degrade themselves. And also it should remain inert. Okay, it should have a solubility in that one, but it should not have any chemical reaction with the solute. If the chemical reaction is happening, then B plus C will give rise to some D, so some product will form. So we are not concentrating on that product. We want only C as our main product. So in order to do that, the solvent needs to be chemically inert, and at the same time it should be chemically inert to the construction material also. The extraction construction material is there, that cell, extraction cell we can call, that extraction vessel we can call. So if that is reacting with that material, construction material is also, then there is a contamination inside that process. So the solvent should be inert as well as thermally stable. It should be inert for the solute, and it should be inert for the construction material also. Then another properties like viscosity. So what happens if the viscosity is very high? If the viscosity very high, the pumping cost will be very high, and at the same time the dispersion of one phase to another phase will be very low. If there is no dispersion, there is no separation by this extraction process. So viscosity should be very low, and vapor pressure should be very low in order to have a better storage condition. Better storage conditions or a health and safety issues. So this viscosity, this vapor pressure should be very low. Then next one is this freezing point. This freezing point needs to be very low in order to have a better storage condition. If it is freezing at that point, what happens? The storage will be very difficult. And then non-flammability, it should be non-flammable. So health and safety conditions, if it's flammable, then it is hazardous. Then non-toxic, it should not be toxic, and it should be available readily at low cost or a very less cost. These are the properties. Based on this one, we have to select the solvent. One is the solubility, next one is the selectivity, distribution coefficient, recoverability, density, interfacial tension, chemical reactivity, and viscosity, vapor pressure, freezing point, inflammable, non-toxic, and cost should be very low. These are the properties. Based on this, we have to select the solvent. Okay, I hope you understood. In the next class, if you have any doubt, you can ask me.